Hello, my name is Yeonsoo. I'll introduce our off-the-chain execution environment for scalable testing and profiling of smart contracts. This is joint work between Yonsei University and the University of Sydney. Transaction replay is important for auditing, testing, profiling, and debugging of smart contracts. The challenge with transaction replay is to retrieve the historical state that the transaction was originally executed on. Transaction execution is defined as a series of sequential state transitions on the world state. To replay a transaction in block N, the EVM requires the state at block n-1 as the input. To retrieve state n-1, the testing environment should download blocks from the Genesis block to block n-1 and execute their transactions sequentially. Ethereum clients like Geth synchronize to the tip of the chain. Executing from a historical state other than the current state is not considered in the design of the Ethereum protocol. The closest approaches to ours are Geth archive nodes and Geth full nodes in fast sync mode. Geth archive nodes store the entire history of world states in the archive database, so it can be used to retrieve the state at an arbitrary block for transaction replay. In practice, a Geth archive node requires enormous time and space to create and maintain the archive database. But archive nodes show very low throughput with transaction replay, which makes it pointless to maintain an archive database for transaction replay. A Geth full node in fast sync mode downloads the intermediate state at block M and executes transactions beginning from block M instead of the Genesis block. In practice, a Geth full node requires less space and time compared to a Geth archive node. However, the Geth full node still requires some time to process intermediate blocks from block M to block n-1, and space to store a complete world state with all accounts from the previous blocks. In the worst case, if block N is far behind the tip of the chain, then no peer will be available to provide an intermediate state for fast syncing. Efficient transaction replay is an unsolved problem. A recent survey among smart contract developers revealed severe problems related to the replay of transactions. For instance, the EVM's inability to run transactions in parallel is a major challenge for the timely reaction and verification of transactions. Developers are further challenged by the limitations of current testing and debugging tools for smart contracts, and demand an easy way of forking mainnets for testing purposes. Our contribution is a new testing environment for smart contracts on the Ethereum blockchain for fast re-execution of historical transactions. First, we designed a record replay mechanism to enable transaction execution off the chain in isolation and at scale. Second, we reorganized the Ethereum world state into transaction-relevant substates, which contain minimum information required to faithfully replay a transaction. Third, we evaluated the proposed approach with 3 use cases: a regression tester for hard forks, a dead code analysis, and a program fuzzer for smart contracts. Our solution first records transactions by importing all blocks from the Genesis up to the tip of the chain. Recorded transactions include full cryptographic verification to simulate on-chain features in the off-the-chain environment. For each transaction, the recorder captures the historical state from before and after the transaction on the chain. Substates are restricted to the subset of the world state required to faithfully replay the transaction. Therefore, substates have no dependency on earlier transactions on the chain. Our recorder stores substate records in the substate database. Transaction replay from the substate database is conducted off the chain in isolation. Our replayer mocks on-chain features to execute transactions without the overhead of the distributed system. Absence of dependencies on prior transactions allows instant replay of historical transactions off the chain in isolation and at scale. This is how our recorder works. First, the recorder collects environment parameters from the block and message. During transaction execution, the recorder traces the access indices of key value pairs, which consist of account addresses and storage keys. Next, the recorder collects access values and stores the resulting key value pairs as so-called input-output tuples. Then, the recorder collects the transaction result, which contains status code, event logs, and guest uses. Lastly, the recorder stores the collected information in the form of input-output substates in the substate database. Here is an example of input-output tuples from a token transfer of 10 units at key 2 of Ethereum account address 1 to key 2 of Ethereum account address 2. The recorder traces access indices, address 1 key 2 and address 2 key 2, the second step. When the execution finishes, the recorder collects the input-output tuples from the input and output states of the transaction. Then, the recorder stores those tuples in the substate record, together with environment parameters and the transaction result. Our substate replayer loads a substate and replays the transactions of the chain. First, the replayer copies the input substate from the substate database to an in-memory VM context. Then, the replayer executes the transaction in isolation, traces access indices, and captures its output substate as the recorder did. Lastly, the replayer validates the replay of the transaction by comparing the replay output substate with the recorded output substate. If access indices or the replay output differ from the recorded output, the replayer will raise an exception. Consider the previous token transfer example. If the EVM stores 0 instead of 15 at address 1 key 2, the trace value in the replay output differs from the recorded output. So assert equal will fail and raise an exception. Substates are sufficient to replay and validate transactions in isolation. The elimination of dependencies on earlier transactions enables transaction replay at scale. We evaluated our off-the-chain test environment with the initial 9 million blocks from the Ethereum blockchain containing 590 million transactions. The replayer finished without raising an exception, which signifies a 100% replay accuracy. This result shows that the substate database saved about 59% of disk space compared to a Geth full node. The left table shows that our replayer is 4.54 times faster than the Geth full node with a single thread. The right figure shows the scalability of the replayer on our multi-core evaluation platform. When scaled to 44 cores, replay of 590 million transactions finishes within 6 hours. To demonstrate the effectiveness and efficiency of our record replay infrastructure for dynamic analysis, we introduced 3 use cases for our substate replayer: a metric use case, Fuzzer use case, and the assessment of hard forks. We implemented a metric for wasteful instructions. Wasteful instructions have no lasting side effect on the blockchain state. We built an algorithm that propagates the necessity of instructions in the value graph in a backwards fashion. In this graph, as store and return instructions, and instructions connected to these two are considered necessary. The analysis of wasteful instructions took 75 hours for 9 million blocks. We observed increasing wasteful instruction ratios and wasted gas per transaction with later blocks. Transaction in the range from 8 to 9 million on average contains 50% of wasteful instructions and 25,000 wasteful gas. Fuzzing is a popular means to assess software quality and exercise a program under test with many randomized inputs. Low-performing fuzzers limit the effectiveness of a fuzzing campaign and may result in many false negatives. To demonstrate the effectiveness of the parallel replay mechanism for fuzzing, we integrated our off-the-chain replayer with contract fuzzer. We use substates from the mainnet for our evaluation. Our replayer already shows higher throughput with a single thread because substates are more lightweight than testnets. Multi-threaded replay scales fuzzing campaigns on multi-core architecture, which is not possible with the original contract fuzzer. The Ethereum specification has been updated over the years via hard fork. Hard forks may cause problems with already deployed contracts because they are immutable. In a recent survey, developers stated that maintaining backward compatibility is of utmost importance with blockchain platforms. Therefore, it is important to assess the effects of new hard forks on existing contracts before they become effective on the mainnet. This table shows the number of assessed transactions per hard fork, the effects of hard forks, and the percentage of affected and unaffected transactions. It took about 15 hours to assess hard forks with a total of 529 millions of transactions executed. The sum of column EVM runtime exception and output change indicates effects of hard forks on the execution path of smart contracts. The column gas usage change indicates the effects on gas consumption. 3 hard forks marked by red boxes have the highest ratios of effects on both execution path and gas consumption. These hard forks mainly increased gas costs of EVM instructions, so updating the gas system is likely the main cause of problems on already deployed contracts. In conclusion, our work proposes a new infrastructure for the lightweight execution of smart contracts at scale, multi-threaded, and in isolation. We were able to execute all available smart contracts from the Ethereum mainnet 4.54 times faster than a Geth full node with a single thread, and 50.03 times faster on 44 cores. Our infrastructure is highly suitable for scenarios that require the fast and repeated execution of smart contracts. We have demonstrated the application of our testing and profiling infrastructure through 3 use cases. Our infrastructure scales for the whole blockchain, which has not been possible with prior approaches. This is the end of my presentation. Thank you very much for attending. If you have any questions, please ask in the coming live Q&A session or contact me via email. Thank you.